Okay, so today we're gonna go through a question that was raised in our previous video. We're gonna try to explain it, and after that we're gonna go through um probabilistic problem using the Bayes theorem, right? And see how we can approach that from a logical perspective to hopefully get like a full understanding of what the Bayes theorem is doing and why it's so important to use in the probability world, right? And it can get used like applied in so many different fields, right? So let's start by the question that was raised. I was asked by someone that why did I call the probability of A and B, which is probability of A times probability of B if A happens. Why did I call this the Bayes theorem, right? I make that statement in my previous video. So remember that this is just probability of B in case they are independent, right? But so why did I call this the Bayes theorem? Well, the reason why I called it is that the Bayes theorem actually comes from here, right? If you solve for probability of B and A, you're gonna end up having the formula that most of the probability textbooks or like when you Google it are gonna have, right? So let's just do it. So let's solve for probability of B if A happens, right? That's gonna be equal to the probability of A and B over the probability of A. And something to know here is that because this is an intersection, the order of the factors doesn't affect the result because they're cumulative from each other, right? So this is actually the same thing as saying probability of B and A. And the reason why I'm doing that is because if I expand this, I will just cancel A with A. And yeah, that's true. Probability of B, if A happens, is equal to probability of B if A happens, but you don't go anywhere with that, right? That's why we want to change the format a little bit. So this will be end up being probability of B if A happens is equal to probability of B times probability of A if B happens over probability of A. And this is what you'll find in any probability textbook, right? This is the format of the Bayes theorem. But as you could see, it came from the same place. That's why I made that statement last time. Now let's go through like a quick example here of how to use this formula from a logical perspective, right? So let's assume that there's a disease that 1% of the population has it, okay? So the probability of disease D, let's call it D, is equal to 1%, okay? And let's say that we have a test that is 99% accurate, okay? That means that the probability that you test positive if you have the disease is equal to 99% of the time, 99% probability, okay? So you might think that 99% is pretty good, but let's dive into it and try to understand what would be the probability of having the disease if you test positive. These two are not the same. A lot of people think they're the same, but they're not the same, right? This is actually a most important question to ask. What is the probability of me having the disease if I test positive, right? Does this thing here doesn't tell me much, right? Like, okay, I know I have the disease. What are the chances of me testing positive? Well, yeah, 99% of the time, but that you are not learning anything about that, right? But this is like you don't know if you have the disease, right? Or like you like for example, this one you have the disease, but you don't know, right? You first know that you tested positive. You want to know if you had the disease or not, right? So I think this is the most important question to do. And as always, we're gonna approach this question with proportions because again, probability is easier to understand when you look at proportions. So as always, let's start with our sample space. Let's have this square as our sample space. What do you know? Well, you know that 1% of the population has the disease, right? So let's just draw that out. Okay, so this is gonna be my sick people, and over here we're gonna have our healthy people. Okay. what else do we know? Well, we know that our test is 99% accurate, right? Meaning that the people that is sick are gonna have a positive test 99% of the time, and kind of like a false positive just 1% of the time. And same with the people that is healthy, right? So you're gonna have like a positive test only 1% of the time, which is like a false positive pretty much. And you're gonna have, you're gonna test negative 99% of the time because you're healthy, right? This is what this information is telling us pretty much. Okay, so now having that said, let's keep solving this. What is the probability of having the disease if you tested positive? How logically can we how can we solve this from a logical perspective? Okay, so what this is pretty much telling you is that you already know you tested positive. Okay, so that's a fact. You already know you tested positive. What is the probability that you test positive? Well, you have two options, right? The first option is that, well, that you actually have the disease and you tested positive, right? And the other option is that, well, you're actually healthy, but you tested positive. The test made a mistake, right? And you're comparing that to a probability that you're actually sick and tested positive, which is the first rectangle here. And this is simply saying, right? So how do we get this rectangle? Again, proportions. You have your entire sample space. You know that 1% of the population is sick. So this is 1% times 99% accuracy. Okay, this is over, well, this rectangle is same as this rectangle, so we're just gonna copy that. Plus this big rectangle here. And what is this? Well, the 99% of the population, right? And they're gonna test positive incorrectly because the test is making a mistake just 1% of the time. And this, you will end up having that this is equal to 50%. Okay? And well, at the beginning, let's remember that the accuracy of the test is 99%. And then if you ask this question, look how things change, right? Is in probability and statistics can tell you what are the good questions to ask and how to somehow quantify that in probability, right? And you can get, this principle applied to manufacturing, to quality controls, and all of that, right? We can have more examples in the real world of an engineer if you guys want to. But what I'm trying to get at is very important to understand the principles of probability and statistics. And this has been taught like as a, very simple principle, but like not many people know how to apply it and why this formula is so useful. So I hope you like the video and I hope it helps you out.